This video is for both section 2.2 and 2.3, an introduction of limits and talking about how to calculate those limits. Well, let's get started. So to find the tangent to a curve or the velocity of an object, we now turn our attention to limits in general and numerical and graphical methods for computing them. We spent a lot of time on this in 2.1, estimating and approaching a value in order to estimate the slope of the tangent line. Let's investigate the behavior of the function f defined by the following. So it's a parabola, and we're looking for the values near an x equals 2. The following table gives the values for the particular function that we just looked at and the values that are close to 2 but not exactly equal to 2. So we see that we start from the left side as we were practicing in class last week, and we are approaching a value of 2. The y value is approaching, looks like 4. Here we come from the right side, we start with 3 and we get closer and closer to 2 from the right side of the number line, and it's also approaching a value of 4. And we can say that the limit from the left and the right are approaching the same value 4, and therefore the limit exists and the limit is 4. If we're looking at a graph, here's 2. Now we could actually put in 2, and 2 squared minus 2 plus 2 is equal to 4. So we do know that the y value is 4. So this is almost trivial that we're doing an example where the limit can be directly calculated, but that's the case sometimes. But graphically, we can see as we approach from the left, we were approaching the value of 4. We approach from the right, and the y value is also 4, and therefore the limit exists. In fact, it appears that we can make the values of the function as close as we like to 4 by taking x sufficiently close to 2. We express this by saying the limit of the function f of x equals x squared minus x plus 2 as x approaches 2 is equal to 4. Literally, that is the long English translation of this mathematical statement. That's why mathematicians love our symbols, because we do not write all of this English. We write it in very concise symbol form. In general, we use the following notation. The limit as x approaches a of the function f of x is equal to some number L. Now, in the figure, we show graphs of 3 functions. Note that in part C, f of a is not defined, and in part B, f of a is not equal to the limit. But in each case, regardless of what happens at A, it is true that the limit is equal to L. So in A, we are trying to find the limit as we approach A on the x-axis, and we see that from the left and the right, it matches, and it would be L. Over here in B, what we're saying is if you look right there, there's a little blue dot that is actually the y value because there's a hole in the function. But if we were looking at the limit from the left and the right, we would not know that there was a hole at the function. We would say that the limit approaches L without knowing that the y value is different. And here, same thing, except there is no y value. It's just a hole, meaning that that value would cause a problem, such as putting in a value of x that would give you a 0 in a denominator of a function. There would be a hole there, and there would not be a y value somewhere else. It just wouldn't exist. But the limit still exists because the left and the right still approach the same y value L. Guess the value of this limit. Okay, so if we look at this limit, if we try to directly substitute 1 in for x, we would see that that produces a 0 in the denominator, which hopefully, without much explanation, you guys know that that is bad. So we would use the same idea we did when we were trying to squeeze or find approaching the what we would expect the slope of the tangent line to be by finding values on the left side of 1 and finding values on the right side of 1. So I can look at these y values, and as I approach 1 from the left side, it looks like I'm getting 2.5. I approach 1 from the right side, I'm also approaching 0.5, and therefore my estimate would be that the y value is approaching 0.5, even if the y value doesn't actually exist, which in this case it doesn't because there's a hole there, but there's still a limit. Now, unlike with the slope of the tangent line where I showed you had to come from the left and the right side, but it wasn't as prominent of why you had to do both. Here, it is extremely important because many functions are going to be step functions where their graph might not meet up in the same spot. So the limit from the left side may not equal the limit from the right side, and therefore we'd have to conclude that the limit does not exist. So if we're taking a look at the graph, again, there's a hole because one actually creates a zero in the denominator, which is very bad. So even though the limit approaches a y value of zero point 0.5, the actual y value does not exist. This new function still has the same limit as x approaches 1. But now, well, we're not showing the function, but let's say it's a different function where you can actually have an output. Well, actually, we do have a function. It's here. There's the step function. And we're saying that at exactly 1, the output is 2. So that gives you an extra point here. Now, again, the limit is still 0.5 because we are not trying to find the y value exactly by direct substitution. We were just taking the limit from the left and the right. It's still going to give us a 0.5. If we're trying to find the limit of this particular function, there is no denominator that's going to cause a 0, and it is not a square root where we have to worry about negatives under the square root, so direct substitution would be perfectly fine. So 3 squared is 9 plus 5 times 3, which is 15. So 9 plus 15 gives us 24 minus 1 is 23. So we would state that the limit as x approaches 3 of x squared plus 5x minus 1 is 23. And that was just done by simple direct substitution, which is okay to do. Now, we do have one-sided limits. So, like I was saying, when the left limit does not match the right limit, they're in different spaces, the limit doesn't exist overall. But if you were specifically only looking for a one-sided limit, you were only looking for a limit approaching from the left or approaching from the right, then that limit exists as long as it's approaching a real number. So if we take a look at the Heaviside function, which is defined by the function is equal to 0 if your input is less than 0, and the output is equal to 1 if your input is greater than or equal to 0. Then you would say that if you were to approach the limit of 0 from the left side, you would get 0. But if you approach the limit of the function from the right side, notice these little notations after. So they're not in front of the numbers, they're after the numbers. So this is from the left, and the little plus sign means from the right, you would get a different limit because that is the breaking point. They break at 0. So coming from the left, you're approaching 0, but coming from the right, you're approaching 1. Okay, so notice the symbols. The little negative sign indicates you are literally coming from the left side. So as you're reading, you're looking all the way to the left and you're following the function. And in the little plus sign means look to the right and follow the function up into the x value in question. We should write the left-handed limits with the limit as x approaches a from the left of a function is equal to L. Or the limit as x approaches a from the right of this function is equal to L. So if we're looking from here, and I am looking to approach x from the left, I'm literally going to start over here and work my way towards x from the left. So working my way here to find that limit. But if I am approaching, I'm approaching A, sorry, over here to find the limit. And if I'm going from the right side, I'm literally going to start tracing the function on the right side until I reach my magical number on the x-axis. By comparing definition 1 with the definitions of one-sided limits, we can see the following is true. The limit will exist with no direction given if and only if the left and the right limits are the same. They approach the same value. So again, we can have a left limit that exists even though it's different from the right. We can have a right limit that exists that even though it's different from the left. But if we have a non-directionally labeled limit, the left and the right must be the same in order for the overall limit with no direction indicated to exist. The graph of the function g is shown, and we're going to use it to find these following limits. So the first one, using the graph alone, find the limit as we approach positive 2 from the left side. So first thing you're going to want to do is find +2 on the x-axis. And then what we want to do, so think of this almost like a brick wall. You're going to smack right into it. It tells us to trace from the left. So I'm going to start over here on the left, and I'm going to approach 2 from the left, and I see that I am approaching a y value of 3 as I approach 2 from the left. Now, if I want to do the same thing, but I'm approaching from the right side, I'm going to start over here and trace my function. And again, I'm coming up to the vertical, hitting that brick wall at 2. But what I'm looking for the limit is the y value. So if I'm approaching the same value x, but from the right side, I do not have the same limit as when I approached from the left. I'm actually approaching a 1 when I approach from the right side. So then if I'm looking at part C, does the limit exist at +2 since the left limit is equal to 3 and the right limit is equal to 1, and 3 definitely does not equal 1, you would say does not exist. Or very commonly, the abbreviation would be capital D, capital N, capital E. DNE does not exist. Let's take the limit as we approach 5 on the x-axis from the left. So here's 5. We're going to approach from the left. So I'm going to trace here until I smack into 5. And I see that the y value is 2. So the limit as we approach from the left is 2. When we approach from the right, we actually get the same limit because they're both approaching 2 as we approach 5 on the x-axis. But if I am looking at the limit overall, this time does exist. It is 2. It is the same as the left and the right as long as they are equal. But if I was to ask you what the y value is at exactly 2 for this function, the y value is 1. So the limit doesn't always tell you what the y value is. It can only tell you what the function is approaching. Now I want to practice sketching a piecewise function with you so that you guys can recall. This is back from algebra or pre-calc, but the more that we understand how to create a piecewise function, the easier it is for us to understand how to read it. So I am going to jump over to my whiteboard so that we can draw this out together. Okay, so I'm looking down because I'm using my iPad now. All right, so we want to look at the function. And I just want to make sure that you guys are still seeing my whiteboard. So the function is f of x is equal to, it's going to be equal to a function x when we are looking at the inputs less than -1. We are going to use an upside down parabola when the input is between -1 including, but not include, oh, and including 0. And then we are going to use the square root function when our x is really big, bigger than 0, that is. Now, I know this isn't the neatest looking function that I'm writing, but that's why it's in the PowerPoint. So let's start to graph this. So, you know what? Let me write this over, just to be a little smaller, so I can actually graph. So let me just write this over real quick. So we're looking at a function, and we have x negative x squared and square root of x, and our restrictions. This is when x is less than -1. This is when x is between -1 and 0, and this is when x is greater than 0. So let's draw this in. And I'm going to draw these 3 functions. So we know that x is a linear line that goes through the origin and meets all the points like 1, 1, 2, 2, 3, 3, 4, 4, that kind of thing. And since it exists on the left side where we are less than -1, here's -1, -2, -3, -4, -5. Let me just get some little scabies in here. Okay, so I want to choose a color. I'm going to choose red. And this, because this is strictly less than here, that means that it's going to be an open circle. And I'm going to put an open circle on the point that crosses the line y equals x at -1. So if I put -1 in for x, the output is also -1. So this is the point -1, 1 that is on that line. And it says use the line x for every x value less than -1. So that's just drawing to the left. So the line y equals x looks like this, where it hits all the points -2, 2, -3, 3, -4, 4, and so on. Now I'm going to move for my next color. Let's do blue. -x² is an upside down parabola, and it says use the upside down parabola between -1 and 0, but inclusive. So inclusive, notice that we have less than or equal to and less than or equal to, which means a closed circle at -1 and 0. So if I put -1 into -x², I get -1 squared, which is +1, and then multiplied by -1 is also -1. So again, this also has a point -1, -1. So it's going to overlap, but it's going to be colored in this time. And then the point 0, if I put 0 into -x², it comes out to be 0. And this is actually a very small piece of the function. So I'm going to draw the function. It's an upside down parabola, so it has this tiny little half smirk upside down frown. Let's get another color. So my next color I'm going to do is green, and that's going to be the square root function, which we are going to use greater than 0 on the x-axis. There's no equal to sign, so we'll be using an open circle. If I put 0 into the function, the square root of 0 is 0. So I will show an open circle at 0. And then I will use this square root function for every value of x bigger than 0. So this is the piecewise function as a whole, but you would look for the outputs using the given functions based on which x's are going in. If your x's are less than -1, you would be looking for the line for your outputs. If the x's are between -1 and 0 inclusive, you would look for the parabola. If your x's are strictly greater than 0, you would look for the square root function in order to determine what the y value is. Okay, now let me stop sharing my whiteboard and get back to this PowerPoint. We'll have more problems to do on the whiteboard today, so it will be back. That is 2.2, the introduction to limits. And now let's talk about 2.3, which is actually calculating these limits using the limit laws. So here are the limit laws. And you might want to even print this slide. This is in the 2.3 PowerPoint. I've just combined them to make the video easier to use. So we have a function f and a function g. If you are taking the limit of two functions being added together, you can take the limit of each function separately and just add the limits after. Same with subtraction. If you have a multiple of a function, you can multiply the value of the limit after taking the limit of the function without the multiple. You can multiply limits after, you can find the limits of the functions being multiplied and then multiply the value of the limits after, and same with division. So most of the time, 4 and 5 do not hold for many things. This is very strictly in reference to limits. And you'll see that as calc goes on. So that allows us, by using tools, it allows us to solve these types of problems where we don't even have functions. How the heck do we know what the value of f of x plus 5 times g of x is at the value of -2 without an actual formula to calculate? Well, by using the limit laws, we can find the value of the limit of f of x at -2. We can find the value of g of x at -2, then multiply that limit by 5 and add them together. So f of x approaching -2. All right, let's find -2. That's here. Here's -2. F of x is the pink function. So if we're approaching from the left, we're approaching a y value of 1. If we approach from the right, we approach a y value of 1. So the limit of f of x as x approaches -2 is +1. Now let's do the same thing for g. So here's -2 again. So I'm following from the left and I'm approaching a y value of -1. Approach from the right, I approach a y value of -1. So the limit as x approaches -2 of just g of x is -1. So now we have 1 plus 5 times -1. So that's 1 plus a -5. The overall limit is -4. Now for this example, we are multiplying. So again, I'm going to focus on each individual function. I'm going to find the limit as x approaches 1 of f of x. So here we go. Here's +1 on the x-axis. From the left and from the right, we are approaching a y value of 2. And then I do the same thing for g. So here's +1 from, ooh, they're not the same. From the left, I'm approaching a -2. From the right, I'm approaching a -1, which means the limit without a direction indicated does not exist. Therefore, this does not exist. Division. So +2 is right here. So f of x, as we approach +2 from the left and the right, it's approximately 1.5. And for g, from the left and the right, it's 0. So zeros in the denominator, that is against the laws of limits. You cannot do the division rule if the denominator is 0, and therefore this limit also does not exist. And here is all of that I just did out for you verbally is written out for you nice and neatly so that you can read through what I was verbally saying in these solution slides. So if we use the product law repeatedly with g of x is equal to f of x, we can obtain the following law called the power law. Okay, so if you have a function that is being raised to the nth power, you can find the limit of the function and then raise the limit to the nth power, the value of the limit to the nth power. You have a lot of freedom when it comes to limit laws, and they're really important, and they come up again in Calc 2. So this might seem like, oh, okay, there's rules, but in Calc 2, we are going to work with some more difficult improper integrals and series and sequences. And to solve some of them, these limit laws will really come into handy. So when you're taking the limit of a constant function, it's always going to be equal to the constant because it's constant. I know this is the definition of a constant. And if you're taking the limit of just the variable x, you are going to be equal to the value you're approaching, a. Okay, if we now put f of x equal to x in law 6 and law 8, we can also come up with some extra laws. So x to the nth, if we're approaching a, is a to the nth. The nth root of x is going to be equal to the nth root of a. And you can take the square root of a function, an nth root really, of a function before the limit or after, you will still get the same result. So this root law actually does come up. Root and the power law comes up in Calc 2. Keep that in mind. Direct substitution property. If f is a polynomial or rational function and a is in the domain of f, then you should be able to conclude that the limit as x approaches a of the function will be equal to the y value if you direct substitute the a in. Using direct substitution to solve the following limit, literally put the 2 in for x. 2 squared is 4 minus 3 is 1. The limit as x approaches 2 for the function x squared minus 3 is equal to 1. Those are obviously going to be the easiest limits. But, no surprise, direct substitution doesn't always work. So for here, if I put 1 in, I'm going to get a 0 in the denominator. If I put 0 in, I'm going to get a 0 in the denominator. If I put a 0 in, I'm going to put a 0 in the denominator. So direct substitution is bad here. That does not mean the limit does not exist. It just means you got to get more creative. Either you need to go an analytical route and do the numbers, approach 1 from the left side, 0.999, approach 1 from the right side, 1.00001, and look at the table of values to see what the y value is also approaching from both sides. Or in these cases, we can actually use our algebra. So let's do that. Okay, so let's now use our algebra to solve. So if I look at this numerator, I am going to factor the numerator. So if you remember the difference of two squares, that is supposed to be a parenthesis. If you remember the difference of two squares, then x plus 1 times x minus 1 gives you that x squared minus 1. So bring up, if you need to look back in your algebra days, that's from the difference of two squares. Okay, over your denominator of x minus 1. So now, since I've factored the numerator, I can see algebraically these are equivalent, leaving me with just an equivalent algebraic equation of x plus 1. And I can now do a direct substitution by putting 1 in there and getting the limit of 2. Now for the second one, I'm going to have to go to the actual whiteboard for this one because this one's going to be a little bit more work and I'm going to need more room. So let me go to the whiteboard for this. Okay, so the next example is the limit as x approaches 0 of 3 plus x squared minus 9 over x. And we know that the issue is that if did direct substitution as it is right now, we would get a 0 right in the denominator. So what we want to do is we want to actually multiply out the 3 plus x squared. So we are going to do 3 plus, that didn't work out right, that wasn't a 3. 3 plus x times 3 plus x. So recall from your algebra days that you would need to distribute. So this gives us 3 times 3, which is 9, 3 times x, which is 3x, x times 3, which is 3x, and x times x, which is x squared. Combine like terms, we get 9 plus 6x plus x squared for the binomial squared part. So now I'm going to write that in. So I'm still taking the limit as x approaches 0. My numerator is now 9 plus 6x plus x squared minus 9 over x. Now my 9's cancel. Again, my goal is to eliminate the problem in the denominator. So I now have two terms left that both have x's in them. So I'm going to factor out the x. So I'm going to have x times 6 plus x over x. Remember, you can only cancel things when they're connected through multiplication, or you're doing very bad algebra. And now I have an equivalent statement where I can do a direct substitution with what's left by placing 0 in the formula that's left, 6 plus x, which is 6 plus 0. And that leaves me with a limit of 6. Now, the last example that was on that slide, the limit as x approaches 0 of the square root of x plus 4 minus 2 outside of the square root all over x. Oh, let me write that again, but this time in the corner of the screen, not the center. Square root of x plus 4 minus 2 over x. Okay. In this particular problem, again, our goal is to get rid of the x in the denominator as it is the problem. Again, another way to do this is the analytical approach, approaching values from the left side of 0, approaching values from the right side of 0. But I want to make sure we also know there's algebraic approach as well. So this one, you may or may not have covered conjugates in pre-calc. Hopefully you did. But conjugates is essentially multiplying by a form of 1. Now this is an expression, it doesn't have an equal sign, so you can't multiply by anything that will actually change the equation. But we know if we multiply by 1 in anything, that does not actually change the value of the function. So I just have to make sure I'm multiplying by the same thing over the same thing, which is a form of 1. Now the conjugate says use the square root, same exact square root, but change the sign of the value outside here. So this is going to be a +2, and you have to multiply by the same thing over the same thing in order for it to be a 1. Therefore, you're not officially changing anything value-wise. Okay, so now think of these as a binomial times a binomial, and we have to distribute just like we just did in the last example. So let me put this limit part out because we haven't taken the limit yet. So if I stop writing it, then sometimes we forget to actually do that part in the end. So we have the square root times the square root. So same thing times the same thing gives you that thing squared. So we have the square root of x plus 4 times itself, which essentially is its squared. And then we have the square root of x plus 4 times 2, so plus 2 square roots of x plus 4. Okay, now we're moving over to this -2. -2 times the square root, so that gives us -2 square root of x plus 4. And -2 times +2 gives us -4. All over x times the square root of x plus 4 plus 2. Now, I don't care about the denominator right now, and I definitely don't want to distribute this out because my goal is to cancel that x at some point. Now, what's cool about using the conjugate works this way every time. That is the whole point of multiplying by conjugate, is that you squaring a square root, meaning they cancel, so that square root's gone. This is a positive and a negative form of the exact same term, so they cancel. That will happen every time as long as you properly set up your conjugate. So now we're still trying to take the limit as x approaches 0. Now we just have x plus 4 because the square root and the square canceled each other, minus 4, all over this fairly ugly denominator, but again, it won't matter in the end how ugly it is. Ugh. Okay, it got uglier because I can't write on this thing. Here we go, x plus 4 plus 2. Now we see a positive 4 and a negative 4 in the numerator, so that cancels. And now we're left with just an x in the numerator and an x being multiplied in the denominator, so we're allowed to cancel those as well. So we have gotten down, finally we've gotten rid of our problem child, which is the solo x in the denominator. And now we're taking the limit of this equivalent expression. Now there's still an x in the denominator, but is no longer alone. So putting a 0 into this particular denominator doesn't create a problem at all. So we get 1 over the square root of 4, because 0 plus 4 is 4, plus 2, which gives us 1 over 2 plus 2, or a limit of 1/4. That's supposed to be an equal sign, not a negative sign. 1/4 is our limit. And we did this through algebra by using conjugates. Really useful. So you're going to want to remember this example. Let's head back to our PowerPoint now. Okay, so we just did these 3 examples out. Okay, so some limits are best calculated by first finding the left and the right-hand limits and then follow through. And other times we can use algebraic methods or graphical methods to help us. Okay, so these theorems are stating that in theorem 2, when x is near a, except possibly at a, the limits of f and g both exist as x approaches a. But more importantly, I want to focus on the squeeze theorem. So in some cases, we are working with functions that are not polynomials, or rational functions, and therefore algebraic manipulation doesn't really work, but we still might have the same problem with direct substitution. For example, if I am looking at the example limit of x squared of sine of 1 over x as x approaches 0. Now, as we can see, if I put 0 in directly, I get an of 1 over x. So I can't do a direct substitution, and there's really no algebraic manipulation. We have a trig function. How the heck are we supposed to algebraically manipulate a trig function? So in the case we're working with a function that can't easily be manipulated, we need to use what's called the squeeze theorem. So the squeeze theorem says, start with a fact. Okay, so my fact is that the function sine of 1 over x is squeezed between two values. So if you look at the sine function, this particular sine function bounces between the values of -1 and 1. And you would know that by just graphing or by knowing a little bit about the sine function itself. Now, notice how I set this up so that it's I focused on the part of the original equation that I knew something about, and it was squeezed between two numbers. So now my goal is to multiply all sides by what I'm missing, which is this x squared. So if I multiply all sides by x squared, then what I result in is that x squared, negative x squared, is less than or equal to x squared times the sine of 1 over x, which is less than or equal to positive x squared. I know it's messy, I'm sorry. Now the squeeze theorem says now take the limits of the far left function and the far right function. So if I take the limit well, that's annoying. I can't just erase easily. I have to keep hitting this erasey button. Hold on. I'm trying to give myself more room. But the erase feature on this is not that great. Almost there. Okay, close enough. So now if I take the limit as x approaches 0 of negative x squared, I would find that I would approach the value of 0. And if I take the limit as x approaches 0 of the positive x squared, I would also see that the limit is equal to 0. So now what I'm seeing is that 0 is less than or equal to the limit that I'm looking for as x approaches 0 of this sine function. You know what? Hold on. Let's just go to the whiteboard real quick because this is getting messy. Yeah, okay. So what we're doing is we showed that negative x squared is a function that's less than or equal to x squared sine of 1 over x, which is less than or equal to the positive function x squared. We built that from a fact. So we know that this is true because we started with a fact. Now, when we took the limit as x approaches 0 of the function on the far left, we put 0 in for x and we get a limit of 0. We take the limit as x approaches 0 for the function on the far right, and we put 0 in for x, we also get 0. So what we're seeing is that 0 is less than or equal to the limit as x approaches 0 of the function that we couldn't take a direct substitution to, which is also less than or equal to the limit of the right. So because the left that's less than is 0 and the right that's greater than is 0, then we can conclude that this limit is approximately 0 as well, as we have squeezed it between two limits. Okay, that concludes our 2.2 and 2.3 for this week.